Space feels like a perfectly smooth, unbroken fabric. From the orbits of planets to the path of a falling leaf, our entire experience of reality is built on this assumption of seamless continuity. This view is not just intuition, it is the formal bedrock of physics, from Newton's absolute space to Einstein's elegant warping of spacetime. We have written the cosmos in the language of the infinite and the infinitesimal, trusting that space can be divided forever into smaller and smaller pieces. But what if that trust is misplaced? What if, upon zooming in far enough, the smooth fabric of reality dissolves into a grainy, pixelated truth? This is not a minor tweak to a theory. It is a revelation that would shatter our foundational models, force us to reinvent mathematics, and redefine the origin of everything. By the end of this exploration, you will understand how the potential granularity of space could solve physics' greatest paradoxes while creating profound new mysteries of its own. We will confront what happens to black holes without singularities, to motion without infinite steps, and to a universe that may have bounced instead of beginning. How solid does your reality feel when you consider it might be built from the tiniest of grains? This smooth, unbroken fabric of space is not a modern invention. It is a legacy we inherited from the very birth of science. When Isaac Newton formulated his laws of motion and universal gravitation, he required a stage for the cosmic drama to unfold. That stage was absolute space, a fixed, infinite, and perfectly continuous background against which every object moved. It was an arena of pure geometry, where any distance could be halved, and that half could be halved again forever. This idea of infinite divisibility was not merely convenient, it was mathematically essential. The calculus Newton invented, the very language of change and motion, relies entirely on the concept of approaching an infinitely small point, a limit that is never quite reached but can be calculated with perfect precision. For centuries, this framework was spectacularly successful. It predicted the orbits of planets, the arc of cannonballs, and the tides of the oceans. Then, Albert Einstein refined the stage itself. In his theory of general relativity, space and time fused into a single entity, spacetime. But crucially, this new fabric remained a smooth, continuous manifold. It could warp and curve in response to mass and energy, creating what we feel as gravity, but it never tore, never pixelated. You could always find a smaller patch of this cosmic fabric to examine. This continuum model became the operational bedrock of our entire physical understanding. Every satellite trajectory we calculate, every gravitational wave we detect, every model of the expanding universe is built upon equations that assume space is fundamentally smooth. It allows for the elegant field theories that describe everything from electromagnetism to the nuclear forces, painting reality as a series of waves on an unbroken sea. The success of this view is so complete that questioning it feels less like scientific inquiry and more like philosophical rebellion. Yet, the very precision of these elegant equations may be masking a deeper, grainier truth. But this elegant, unbroken stage of reality begins to strain under its own perfection. The concept of infinite divisibility, so essential to our mathematics, creates puzzles that have lingered for millennia. Take the ancient thought experiment of Zeno's paradox. To cross a room, you must first cross half the distance, then half of the remaining distance, then half again, and so on, creating an infinite number of steps to complete a finite journey. If space is perfectly continuous, motion itself becomes a bewildering sequence of an infinite number of tasks completed in a finite time. Our experience tells us we can walk across a room, so we dismiss the paradox as a trick of logic. Yet it whispers a deeper question. What if the paradox is not a flaw in our reasoning, but a clue about the nature of space? What if we cannot divide a distance forever, because eventually we hit a fundamental grain, a smallest possible step? This philosophical hint found its scientific echo in the 20th century with the birth of quantum mechanics. Here, in the realm of the very small, smoothness began to crack. Scientists discovered that properties we thought were continuous, like the energy of an electron orbiting an atom, are not. Energy comes in discrete packets or quanta. An electron can exist in this energy level or that one, but never in between. It jumps, it clicks from one state to another without traversing the smooth gradient in between. This was the first major crack in the facade of a perfectly continuous universe. Then came the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the precise position and the precise momentum of a particle. The more you pin down its location, the more its motion becomes a blur of possibilities. This is not a limitation of our measuring tools, it is a fundamental feature of reality. It suggests that at the tiniest scales, the very concepts of a definite position and a smooth path begin to lose their meaning. The universe appears pixelated in its properties. So we have a profound tension. General relativity describes the cosmos as a smooth, curving geometric fabric. Quantum mechanics describes the particles within it as jumping between discrete states on a fuzzy, uncertain substrate. Both theories are spectacularly successful in their own domains, but they refuse to be merged into one coherent picture. This decades-long struggle to create a theory of quantum gravity is perhaps the biggest clue of all. The violent disagreement between our two best descriptions of reality hints that one of their core assumptions is wrong. Many physicists now suspect the culprit is the assumed smooth continuity of spacetime itself. If the energy of an atom is granular, and if position itself is fundamentally fuzzy, then why would the stage upon which these events play out remain perfectly smooth and infinitely divisible? The quest to unite gravity with the quantum world is in essence a search for the grain of the cosmic fabric. This profound tension between the smooth and the grainy points toward a specific frontier. Deep within the mathematics of our two great theories lies a set of numbers so vanishingly small they seem almost mythical. These are the Planck units, named for physicist Max Planck, and they mark the scale where our current understanding of reality dissolves into pure speculation. The most famous is the Planck length. It is approximately 1.6 times 10 to the negative 35 meters. To call this small is a cosmic understatement. If you enlarged a single atom to the size of the observable universe, the Planck length would still be smaller than a single tree on Earth. This is not merely a tiny distance, it is the hypothesized natural pixel size of spacetime itself. At this scale, the gravitational force becomes as strong as the other fundamental forces, and the quantum fuzziness predicted by Heisenberg would warp spacetime so violently that the very concepts of before and after, here and there, lose all meaning. Our equations for gravity and quantum mechanics both spit out infinities, a sure mathematical sign that we are asking questions our tools cannot answer. Alongside this fundamental length comes a fundamental tick of the clock, the Planck time. This is the time it would take light to travel one Planck length, about 5.39 times 10 to the negative 44 seconds. Within an interval this brief, our notion of a smooth, flowing time evaporates. There may be no shorter duration, no smaller increment of change possible. This suggests time itself might not flow like a river, but click forward in these unimaginably tiny, discrete steps. Finally, there is the Planck energy, an amount so colossal that concentrating it into a volume of one Planck length would create a microscopic black hole. This scale represents the energy at which particles would interact so powerfully that they would probe the very structure of spacetime. Think of it like this. You can study the smooth surface of a pond with a gentle fingertip, but if you strike it with immense force, you might shatter the water into droplets, revealing its underlying molecular nature. The Planck energy is that strike, the level needed to potentially shatter the illusion of smoothness and see the grains of reality. It is crucial to understand that the Planck scale is not proof that spacetime is pixelated. We have no direct experimental evidence of this yet. Instead, it is the ultimate warning sign posted by our current physics. It tells us that below this scale, our maps are blank. The smooth, continuous geometry of general relativity and the probabilistic rules of quantum mechanics cannot both be true here. Something new must take over. For many physicists seeking a theory of quantum gravity, this is the guiding clue. If reality has a fundamental granularity, this is the natural place to look for it. The Planck length, time, and energy provide the concrete dimensions for the universe's potential underlying grid. They are the units of a deeper language, one we have not yet fully deciphered, hinting that our seamless cosmic stage might be constructed from countless, unfathomably small tiles. The Planck scale is the final warning from our current physics, but it is not the end of the story. It is the starting point for a much deeper revolution. To move past this warning sign, we must build a new theory, one that can finally marry the vast cosmic gravity of Einstein with the frenetic quantum world of particles. This quest for a theory of quantum gravity is not merely an academic exercise to tidy up our equations. It is a direct mandate to investigate the very substance of reality. The central conflict is this. In general relativity, spacetime is a dynamic, smooth stage that bends and curves. In quantum field theory, every point in space is a seething hive of activity, filled with temporary particles popping in and out of existence from the underlying quantum fields. These quantum fluctuations are not just noise, they are a fundamental feature of the vacuum itself. Now, try to combine these two ideas. If spacetime is smooth and can be warped by energy, and if every tiny volume of space contains a fluctuating quantum energy, then every point in spacetime should be constantly warping and jittering at random. When physicists try to calculate the gravitational effect of these infinite quantum fluctuations on the smooth spacetime fabric, the mathematics explodes. The equations produce nonsensical infinities, a clear signal that the model is breaking down. It is like trying to describe the surface of a calm pond while simultaneously acknowledging that every molecule of water is vibrating violently. The two descriptions cannot coexist. The smooth continuum cannot withstand the quantum storm. This forces a profound choice. Either our understanding of quantum fields is wrong in this extreme regime, or our picture of spacetime as an infinitely divisible continuum is the illusion. For many leading approaches to quantum gravity, the answer leans decisively toward the latter. To resolve the paradox, to tame the infinities, we must change the rules of the stage itself. Perhaps spacetime is not a smooth fabric that can be divided forever, but is instead woven from fundamental, indivisible threads or grains. A discrete structure with a smallest possible volume and a shortest possible time would provide a natural cutoff. It would mean that quantum fluctuations cannot happen in spaces smaller than a fundamental pixel, preventing the energy from piling up into infinity. In this view, the violent jitter of quantum gravity is smoothed out by the graininess of reality, just as a digital photograph becomes a smooth image when viewed from a distance. The quest for quantum gravity, therefore, is fundamentally a search for the true architecture of spacetime. It asks us to surrender our deepest intuition of a perfectly smooth universe, and to consider that the continuum we have relied on for centuries was only a very good approximation of a much stranger, more granular truth. The most radical solution to this paradox is to discard the smooth stage entirely. One leading candidate theory does exactly this, proposing a universe woven not from a fabric, but from a network of fundamental threads. This is loop quantum gravity. Its core premise is a direct challenge to centuries of thought. Space is not a pre-existing background container. It is the emergent consequence of something more basic. In this view, the fundamental ingredients of reality are tiny, one-dimensional loops of gravitational field, each carrying a discrete unit of area. These loops do not exist in space, they are space. They link together to form a vast, evolving web called a spin network. This network is the quantum state of geometry itself. Think of it like the chainmail of a medieval knight. Up close, you see individual metal rings linked together with clear gaps between them. The armor is not a smooth, continuous sheet of metal, but from a distance, it looks like a solid, flexible surface. In loop quantum gravity, the loops are those fundamental rings, and the smooth spacetime of our everyday experience is the large-scale illusion created by their incredibly dense and dynamic connections. The theory makes a stunningly concrete prediction. Just as energy in an atom is quantized, so too are the properties of space. Area and volume do not come in any possible size. They exist only in specific, discrete units, multiples of the Planck scale. You could not have a volume of 1.5 Planck volumes, just as an electron cannot have 1.5 quanta of energy. Geometry itself clicks from one configuration to another in discrete jumps. This provides the natural cutoff that tames the infinities of quantum gravity. The violent fluctuations are smoothed out because there is no such thing as a region smaller than a single quantum of space for them to wreak havoc within. The spin network is not static. It evolves in time with loops merging and splitting, the entire structure pulsating and changing in these discrete steps. What we perceive as the smooth, curved geometry of general relativity is the large-scale average of this frenetic quantum dance. Loop quantum gravity offers us our first rigorous mathematical picture of a truly pixelated cosmos, a universe where the continuum is replaced by a combinatorial structure of breathtaking simplicity and profound depth. It suggests that if we could peer down to the Planck scale, we would not find a smaller version of smooth space, but a shimmering, dynamic tapestry of interconnected loops, the fundamental code from which reality is compiled. While loop quantum gravity paints a universe of interconnected loops, another profound vision emerges from an even more minimalist principle. Causal set theory asks a startling question. What if the most fundamental thing about reality is not space or time or even geometry, but simply cause and effect? In this framework, the universe is nothing more than a vast collection of discrete events, like individual grains of sand. Each grain is a fundamental point, an irreducible happening. The only structure connecting these grains is a single, powerful relation. This event caused that one. There is no pre-existing stage of spacetime. There is only this cosmic cloud of point events, with a network of causal links between them defining a pure order of before and after. From this sparse, elegant beginning, something miraculous emerges. The smooth, four-dimensional spacetime of our experience is not a primary ingredient. It is a secondary illusion, a story our brains tell to make sense of this underlying causal network. Think of it like the narrative of a novel. The book itself is just a collection of individual words printed in a specific order on separate pages. But when you read it, your mind constructs a continuous, flowing story with characters moving through landscapes over time. The book is the causal set, the discrete events in order. The vivid movie you experience in your mind is the emergent spacetime. In causal set theory, the geometry of the universe, its apparent curvature, and even its dimensionality is not put in by hand. It is derived or born from the sheer number of these fundamental events and the pattern of their causal connections. The volume of a region of spacetime, for instance, is not measured with a ruler. It is simply proportional to the number of elementary grains or events contained within it. More grains means more volume. this approach achieves a breathtaking simplification. It incorporates a fundamental limit on reality, the discreteness of the events themselves, without needing to specify any background grid or geometry. The continuum of space and time is an approximation that becomes valid only when you have a colossal number of these causal elements, just as a movie appears smooth because it displays 24 discrete frames every second. This theory offers a radically different angle on discreteness, one where the flow of time and the expanse of space are not the foundation, but the magnificent and unexpected consequence of a universe built from nothing but countless tiny moments of cause and effect. The most profound consequence of a grainy universe is the end of the infinite. In our current models, the smooth, infinitely divisible continuum of space creates mathematical monsters, points of infinite density that signal a complete breakdown of physics. The most famous of these is the black hole singularity. According to general relativity, when a massive star collapses under its own gravity, all its matter is crushed into a single point of zero volume at the very center. At this singularity, the curvature of spacetime becomes infinite, density becomes infinite, and our equations simply stop making sense. It is a place where the known laws of physics cease to apply, a one-way door to a realm of pure mathematical abstraction. This is deeply unsatisfying. It suggests our best theory of gravity contains its own point of failure, a tear in the cosmic logic where reality winks out of existence. But what if the singularity is not a real physical object, but an artifact of our flawed assumption of infinite smoothness? A discrete spacetime provides the ultimate escape clause. If there is a smallest possible volume, a fundamental quantum of space, then matter cannot be crushed to a point of zero size. It can only be compressed until it occupies this smallest possible region. The result is not an infinite density, but an extraordinarily high yet finite one. The terrifying mathematical singularity is replaced by an extreme but calculable state of matter. Imagine trying to divide a piece of paper in half forever with a pair of scissors. In a continuous world, you could make an infinite number of cuts, creating pieces smaller than any conceivable size. But in our grainy reality, you would eventually reach a point where your scissors are larger than the fundamental pixel of the paper itself. You simply cannot cut any further. The infinite regress is halted by the grain of the material. This is precisely what a minimum length does to a collapsing star. The collapse does not end in a meaningless infinity, but in a fantastically dense, Planck-scale nugget where the quantum nature of gravity itself takes over. This resolution ripples out to solve other profound paradoxes, like the infamous information loss problem in black holes. If the singularity is removed, the door to a complete breakdown of physics is closed, offering new hope that information about what fell in might be preserved or transformed in the quantum structure of the whole itself. Furthermore, this idea extends to the very beginning of everything. The Big Bang in the Standard Model is also a singularity, a moment of infinite density from which the universe emerged. A discrete spacetime suggests there was no true singularity, no infinite beginning. Instead, there may have been a big bounce, a prior phase of cosmic contraction that reached a maximum density set by the Planck scale before rebounding into our expanding universe. The end of the infinitely small does not just tidy up our equations, it rewrites the most dramatic chapters of cosmic history, replacing moments of infinite mystery with epochs of extreme yet knowable physics. The end of the infinite singularity is a monumental shift, but its implications reach far beyond the cosmos's violent extremes. They touch the very act of moving across a room. Remember Zeno's ancient arrow, forever trapped in the logical prison of infinite steps. For over 2 millennia, philosophers and mathematicians dismissed the paradox as a trick of logic, resolved by the calculus of infinite sums. We accept that an infinite series can add up to a finite number, so motion is possible. But this mathematical answer always felt like a workaround, not a true explanation of the physical world. It treated space and time as abstract mathematical continua, not as parts of a tangible reality. What if Zeno was not wrong about the problem, but only about the nature of space? A discrete universe offers a breathtakingly simple physical solution. If there is a smallest possible distance, a fundamental quantum of length, then you cannot divide a journey into an infinite number of steps. There is a finite, albeit astronomically large, number of fundamental steps between here and there. The arrow's flight is not a seamless glide through an infinite number of points. It is a progression from one discrete location to the next, like a stone skipping across a pond, where the water's surface provides the only possible landing points. The paradox evaporates because the premise of infinite divisibility was false. Motion in such a world is not about traversing a smooth gradient. It is about quantum jumps in geometry itself. Each tick of the Planck time clock, the entire spin network or causal set of the universe updates, and the configuration of reality clicks into a new, adjacent state. What we perceive as smooth motion is the emergent result of these discrete transitions. Much like the individual frames of a film create the illusion of fluid movement when played in rapid succession. This reshapes our most basic concept of locality. In a continuous world, two things can be arbitrarily close together. In a grainy universe, there is a final, fundamental notion of next to. Nothing can be closer than 1 pixel of space. This granularity imposes a new kind of order on reality, a digital substrate beneath the analog appearance of our world. The arrow flies because the universe itself is processing, step by fundamental step, from one state to the next. Zeno's paradox, once a philosophical curiosity, becomes a profound clue, a 2,000-year-old hint that our experience of smooth change is the magnificent illusion, and the click of the cosmic clock is the deeper truth. These discrete jumps in geometry would not just change how things move, they would strike at the very heart of physics' most sacred principles. For centuries, we have relied on certain unshakable rules, laws of conservation that seem to govern the cosmos with perfect reliability. The total momentum in a system never changes. The total angular momentum, the spin of things, is always conserved. These are not just convenient observations, they are the foundational pillars upon which every prediction in physics is built. But where do these powerful conservation laws come from? Their origin is one of the most beautiful ideas in all of science, a deep connection known as Noether's theorem. It states that for every continuous symmetry in nature, there is a corresponding conserved quantity. What does that mean? A continuous symmetry is a transformation you can perform smoothly, in infinitely small steps. The fact that the laws of physics are the same here as they are 1 meter over is a continuous symmetry called translation invariance. You can slide an experiment any tiny amount in space, and the outcome remains unchanged. Noether's theorem proves that this perfect, smooth symmetry of space directly leads to the conservation of momentum. Similarly, the fact that physics doesn't care which direction you face, that you can rotate an experiment by any smooth, infinitesimal angle, is a continuous rotational symmetry. This symmetry gives us the conservation of angular momentum. These symmetries and the laws they protect are woven into the very fabric of a continuous, infinitely divisible spacetime. They rely on the idea that you can make an arbitrarily small shift or an arbitrarily tiny turn. But what happens when the fabric itself has a grain? If spacetime is discrete, if there is a smallest possible length and a smallest possible angle, then these perfect, continuous symmetries are broken at the most fundamental level. You cannot rotate a spin network by a fraction of a Planck angle that doesn't exist. You cannot translate something by a distance smaller than the fundamental pixel of space. The perfect, smooth symmetry is replaced by a discrete or granular symmetry. you might only be able to rotate in specific quantum jumps of orientation. You might only be able to shift things in whole number multiples of the fundamental length. This is a seismic shift in our understanding of reality's bedrock. If the continuous symmetries are approximate, then the cherished conservation laws they guarantee might also be approximate. They would hold with incredible precision in our macroscopic world, a consequence of the vast number of grains averaging out to look smooth. But at the extreme energies of the Planck scale, or in exquisitely sensitive experiments, we might detect the tiniest of violations. A particle's momentum might not be perfectly conserved in a high-energy collision, deviating by an amount so small it has escaped all detection so far. The spin of a system might not add up exactly right under conditions that probe the granular structure of space. This is not a suggestion that physics becomes chaotic or random, but that it operates under a different, more fundamental set of rules. The perfect, eternal conservation laws of our textbooks would be revealed as magnificent, emergent approximations, like the smooth curve that emerges from connecting discrete dots on a graph. The universe would still be orderly, but its deepest order would be digital, not analog. The search for these minuscule violations becomes one of the most exciting experimental quests in modern physics, a direct hunt for the grain of spacetime by looking for the faintest crack in what we thought were nature's perfect mirrors. The smooth symmetries of our universe may be more fragile than we thought. One of the most famous pillars of modern physics is the constancy of the speed of light. In Einstein's theory of relativity, light in a vacuum always travels at the same ultimate speed, a cosmic speed limit that is woven into the very geometry of spacetime. This isn't just a rule about light, it's a statement about reality's structure. It emerges from a deep symmetry known as Lorentz invariance, which means the laws of physics look the same to all observers moving at constant speed relative to each other. This symmetry is the mathematical heart of a smooth, continuous spacetime, a fabric that stretches and contracts in just the right way to keep light's speed constant for everyone, everywhere. But if that fabric is actually granular, if it's built from discrete pieces like a digital image, then this perfect, continuous symmetry could have tiny imperfections. Lorentz invariance might be approximate, not absolute. The universe's pixels could introduce a subtle directional grain, a preferred frame of reference at the most fundamental level, breaking the perfect sameness that relativity demands. This theoretical possibility, called Lorentz invariance violation, isn't just a mathematical curiosity. It offers us a direct, experimental path to hunt for the grain of spacetime. The signature would be astonishingly subtle, yet potentially detectable. If the symmetry is broken, then light of different energies might not travel at exactly the same speed across the vast emptiness of space. In a perfectly smooth, Lorentz symmetric universe, a gamma-ray photon and a radio wave, both emitted at the same instant from a cataclysmic event, should arrive at Earth at exactly the same time despite their vastly different energies. But in a grainy universe, the higher energy gamma-ray photon, with its incredibly short wavelength, might interact ever so slightly more with the fine-grained structure of spacetime itself. It could be delayed by a minuscule amount compared to its lower energy counterparts. Over millions or billions of light years, that tiny delay could accumulate into a measurable signal. We are now building observatories capable of this exquisite detective work. When a distant gamma-ray burst explodes, it sends a furious flash of light across the electromagnetic spectrum, from high-energy gamma rays down to radio waves. By meticulously timing the arrival of these different energies, scientists can look for that telltale lag. A consistent delay for higher energy photons from sources at different distances would be like finding a fingerprint on the windowpane of reality, evidence that light does not travel on a perfectly smooth road, but on one with an almost imperceptible texture. It would mean that the most famous constant in physics is not a fundamental feature of the void, but an emergent property of a deeper, discrete architecture. The search for this effect is a quiet revolution, an attempt to read the universe's most fundamental code not by looking at the largest structures, but by listening for the faintest echo in the oldest light. This search for a cosmic grain might hold the key to unlocking one of the universe's most profound secrets. For decades, a single paradox has haunted the intersection of gravity and quantum theory, a puzzle so deep it threatens to rewrite our understanding of reality itself. This is the black hole information paradox. In the smooth, continuous world of classical general relativity, a black hole is a one-way street to oblivion. Anything that crosses its event horizon, the point of no return, is lost forever, crushed into the central singularity. The black hole retains only three simple properties: its mass, its spin, and its electric charge. This presents a catastrophic problem for quantum mechanics, which holds that information about the state of a system can never be truly destroyed. It can be scrambled, transformed, or hidden, but never erased. If you burn a book, the ash and smoke still contain, in principle, the information needed to reconstruct its pages. But in the classical black hole picture, a book and a scrambled collection of its atoms, if they have the same total mass, spin, and charge, become utterly indistinguishable once they fall in. The unique information that was the book is gone. This is the paradox. The smooth geometry of Einstein's theory seems to demand information loss, while the bedrock rules of quantum mechanics forbid it. For 50 years, this conflict has represented a fundamental schism in our understanding of nature. Yet, if spacetime is not a smooth continuum, but has a discrete quantum structure, this terrifying loss may be an illusion. Theories like loop quantum gravity provide a powerful new perspective by giving the event horizon itself a physical texture. In this view, the horizon is not a featureless mathematical boundary. It is a dynamic surface woven from the very fabric of quantum geometry, a tapestry of intersecting loops that carry discrete quanta of area. Just as the pixels on a screen can be arranged in a vast number of patterns to create different images, these fundamental quanta of area on the horizon can be arranged in a staggering number of distinct quantum states. This is not just a theoretical picture, it provides a direct microscopic explanation for one of the greatest discoveries in theoretical physics: black hole entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking realized that a black hole must have an entropy, a measure of disorder or hidden information, proportional to the area of its event horizon. This was a revolutionary idea, suggesting that information was somehow connected to surface area, not volume. But what were the microscopic components counting that entropy? In a smooth spacetime, there was no answer. In loop quantum gravity, the answer is elegant and concrete. The entropy comes from counting the distinct ways the fundamental loops can weave together to form a horizon of a given total area. Each distinct configuration represents a specific microstate, a unique quantum fingerprint for what we classically see as a single, simple black hole. This means the information about what fell into the black hole is not lost inside a mysterious singularity. Instead, it is meticulously encoded on the horizon itself, woven into the complex quantum arrangement of its geometric fabric. The information is transformed, not destroyed, much like the data in a computer is not lost when it is translated from a document into the microscopic magnetic patterns on a hard drive. As the black hole evaporates via Hawking radiation, this horizon structure evolves. The leading idea is that the radiation emitted is not random, but subtly correlated with the encoded information on the horizon, allowing the information to slowly and chaotically leak back out into the universe as the black hole shrinks. The paradox arises from treating the horizon as a smooth, classical surface. When we acknowledge its true, grainy, quantum nature, the path to preserving information becomes clear. The event horizon is not a wall of forgetting, but the universe's most sophisticated quantum hard drive, a shimmering boundary where the story of everything that fell in is forever etched in the language of geometry itself. This quantum tapestry of space has a profound partner, a rhythm that may underpin all of existence. We speak of time as a river, a smooth and ceaseless flow from past to future. This intuition is baked into classical physics, where time is a continuous parameter, a backdrop against which change unfolds in infinitely divisible increments. But if space has a fundamental grain, could time also be pixelated? The mathematics of quantum gravity suggests yes. Just as there is a Planck length, there is a Planck time, the interval it would take light to cross that fundamental distance. This is not just a tiny fraction of a second, it is the hypothesized tick of the universe's most fundamental clock. Time would not flow but click forward in these discrete, indivisible steps. There is no duration shorter than a Planck time, no in-between moment between one tick and the next. The river of time becomes a staircase, and reality advances from one step to another. This transforms a deep philosophical puzzle into a potential physical fact. The elusive present moment, which seems to slip through our fingers in a continuous world, gains a startling definition. It is the single current configuration of the universe's quantum geometry, the now, that exists for one Planck tick before updating to the next. The problem of time in quantum gravity, the difficulty of making time a dynamic variable rather than a static background, is elegantly reframed. Time is not a smooth line, but the sequential ordering of these discrete quantum states of the universe. Causality itself, the chain of cause and effect, is built from this sequence. An event at one tick can be the cause of an event at the very next tick, but it cannot influence something within the same tick, as there is no during to act within. This discrete causality provides a crisp, digital logic to the unfolding of history. For the cosmos, this means the evolution of the universe is not a smooth expansion, but a quantum leap from one geometry to a slightly larger one with each tick. The Big Bang becomes not an explosion from a point, but the first tick in a sequence, perhaps preceded by a prior phase of contraction. Our experience of smooth, flowing time is the magnificent illusion created by the unimaginable frequency of these clicks, just as a movie's motion emerges from 24 static frames every second. We are not floating down a river, but watching the universe's frames refresh, one fundamental moment at a time. The singular beginning of everything is perhaps the most dramatic consequence of a smooth spacetime. In our standard cosmic story, the Big Bang is not just an event, it is the ultimate singularity. Rewind the expansion of the universe, and all matter, energy, and space itself are compressed backward in time toward a single point of infinite density and temperature. At that moment, the curvature of spacetime becomes infinite, and our equations of general relativity simply stop working. It is a boundary, a place where physics surrenders and our story of causality begins. For decades, this singularity has been accepted as the unavoidable starting gun of the cosmos, a moment of pure mystery from which all else flows. But if spacetime is not a smooth continuum that can be crushed to an infinitely small point, this entire narrative transforms. The singularity is not an inevitable conclusion, it is an artifact of an incomplete theory. In a discrete universe governed by the quantum rules of something like loop quantum gravity, there is a powerful new actor on the stage, quantum geometry itself. As the universe contracts toward an unimaginably dense state, it approaches the Planck scale. Here, the fabric of space is not a passive sheet being crumpled. It is a dynamic network of fundamental loops, and this network resists being compressed beyond a certain point. The quantum properties of this geometry generate a powerful repulsive force. Think of it like compressing a spring. You can push it down, but at a certain point, it pushes back with equal and opposite force. In the cosmic contraction, gravity is the hand pushing the spring. The quantum repulsion of the discrete geometry is the spring's inherent resistance. This changes everything. Instead of collapsing to an infinite point, the universe reaches a maximum finite density, a state of extreme quantum gravity, and then rebounds. The Big Bang is replaced by a big bounce. In this profound revision of cosmic history, our expanding universe was not born from a singularity. It emerged from the ashes of a previous cosmic phase, a universe that was contracting under its own gravity. That prior cosmos compressed down to this hot, dense quantum state before the repulsive force of quantum geometry kicked in, reversing the collapse and initiating the expansion we observe today. This is not merely a different starting condition, it is an elimination of the starting point altogether. There may have been no absolute beginning, but an eternal cycle of contraction and expansion, a cosmic heartbeat echoing across eons. The moment of the bounce would have been one of unimaginable energy and temperature, but it would have been a physical event governed by quantum gravitational laws, not a mathematical breakdown. This idea elegantly removes the troubling singularity while offering a new origin story, one where the universe is potentially timeless, eternally recycling through phases of growth and renewal, with our entire cosmic history being just one chapter in a much grander, possibly endless book. This quantum bounce offers a breathtaking vision of cosmic renewal, but it still treats space as a fundamental entity, a thing that contracts and expands. Yet there is an even more radical possibility waiting in the wings. What if space itself is not fundamental at all? What if the three-dimensional continuum we inhabit is not the primary reality, but a grand illusion that emerges from something more basic, something that isn't even spatial? This is the staggering implication of the holographic principle, an idea that reshapes our understanding of reality from the ground up. Its origins are not in wild speculation, but in the hard thermodynamics of black holes. We saw how the entropy, the hidden information of a black hole, is proportional to the area of its event horizon, not the volume of its interior. This was a profound clue. In our everyday world, the information capacity of a region, like the data you can store on a hard drive, scales with its volume. More space means more room for bits. But a black hole, the most extreme object gravity can create, tells us its information content is limited by its surface area. It is as if all the possible things that could be inside the black hole, every star, planet, or book that fell in, are perfectly and completely described by the quantum degrees of freedom painted on its two-dimensional boundary. The holographic principle takes this black hole clue and applies it to the entire universe. It proposes that the information needed to describe everything within any volume of space is entirely encoded on the boundary of that volume. The world you see around you, with its rich three-dimensional depth, is like a magnificent hologram. A hologram is a two-dimensional piece of film that, when illuminated with laser light, projects a fully three-dimensional image. Every point on the film contains information about the entire three-dimensional scene. In the cosmic version, the universe is the three-dimensional projection. The underlying reality is a vast, shimmering network of quantum information living on a distant two-dimensional surface. In this view, the smooth, continuous space of our daily life is not the foundation. It is an emergent, approximate description, a useful story that emerges from the complex interactions of countless bits of information on that lower dimensional surface. This makes the granularity of space a natural and inevitable feature. The underlying quantum system has a finite information density, a limit to how many bits can fit on a given area of the boundary. This finiteness translates directly into a pixelation of the projected three-dimensional world. There is a fundamental limit to how much detail can exist in any region, because the film projecting it has only so many pixels. The continuum is the smooth image we see from a distance, but up close, the individual grains of information become apparent. This turns our intuition inside out. We are not living inside a container of space. We are living inside a projection, an output. The true workings of reality are happening on a distant, abstract surface we can never directly perceive, where the concepts of here and there may not even exist in the way we understand them. Space, with all its apparent solidity and geometry, becomes a secondary phenomenon, a collective effect born from the entanglement of an unimaginable number of quantum bits. The search for the grain of spacetime, therefore, may be the search for the pixel size of the universe's ultimate screen. This holographic projection hints at something even more fundamental than geometry or information. If the universe is a projection from a two-dimensional screen, what is that screen actually doing? One radical answer is that it is computing. The idea that our cosmos might be, at its heart, a vast and ongoing computation is known as the digital physics or computational universe hypothesis. It takes the granularity of spacetime to its logical extreme. If reality is discrete, with a smallest length and a shortest time, then the entire history of the cosmos can be seen as a sequence of states, like frames in a film. Each state is the configuration of the universe at one Planck time tick. The next state is generated from the previous one by applying a set of rules. This is precisely how a cellular automaton works. Imagine a giant multidimensional grid where each cell, each fundamental pixel of reality, can be in one of a finite number of states. With each tick of the cosmic clock, every cell updates its state based on the states of its neighbors, following a simple, universal algorithm. From this breathtakingly basic process, complex patterns emerge, moving, interacting, and evolving. In this view, the laws of physics are not mysterious, eternal equations written on some cosmic tablet. They are the emergent algorithms of this vast computation. Gravity, electromagnetism, the nuclear forces, these are not fundamental forces in the traditional sense, but the large-scale behaviors that arise from the local update rules governing the cosmic grid. What we perceive as a particle, like an electron, is not a tiny, solid ball. It is a stable, self-perpetuating pattern of information, a specific, propagating configuration in the cellular automaton, much like a glider pattern moving across the grid in Conway's Game of Life. Even empty space, the vacuum, is not truly empty. It is the ground state of the computation, the base pattern from which all other excitations arise. This framework offers a stunningly unified picture. It suggests that the search for a theory of everything is not the search for a single, elegant equation, but for the simple, foundational program that the universe is running. The randomness of quantum mechanics could be the result of deeper, deterministic computations that appear random to any internal observer, much like the output of a pseudorandom number generator. The constants of nature, like the speed of light or the strength of gravity, would be parameters of this cosmic code, fixed by the initial conditions and the update rules. This is, of course, a highly speculative vision. It raises profound questions. If the universe is a computation, what is the hardware it runs on? Who or what wrote the initial program? These may be questions that transcend science, venturing into philosophy. Yet, the computational perspective provides a powerful and concrete language for understanding a discrete reality. It reframes our existential quest. We are not just beings made of stardust in a vast, smooth continuum. We might be complex, self-aware patterns of information, transient eddies in the ongoing flow of a cosmic calculation, discovering the very rules that give us form. The universe may not just contain computers, it may, in a very real sense, be one. This computational vision of reality, however, leads to a monumental intellectual challenge. Our entire scientific understanding of the cosmos is written in a language that assumes the exact opposite of a discrete, grainy world. That language is calculus. For over 3 centuries, since the time of Newton and Leibniz, calculus has been the indispensable tool for describing change, motion, and the dynamics of the physical universe. Its power comes from a single, beautiful idea, the concept of the limit. To find the instantaneous velocity of a moving object, you consider its average speed over a smaller and smaller interval of time. You let that interval approach zero, infinitely close without ever quite reaching it. You take a curve and zoom in until it looks like a straight line. This entire mathematical machinery is built on the assumption of perfect continuity, that both space and time are smooth, unbroken, and infinitely divisible. The derivative and the integral, the twin pillars of calculus, are operations that only make sense on a continuum. They allow us to write the elegant differential equations that govern everything from the orbit of Mars to the flow of electricity in a circuit, from the vibration of a guitar string to the expansion of the universe itself. These equations treat reality as a perfectly smooth fabric. But if that fabric is actually a tapestry of discrete threads, if there is a smallest possible length and a shortest possible tick of time, then the very foundation of our mathematical description of nature crumbles. You cannot take a limit that goes smaller than a fundamental pixel. You cannot zoom in past the grain of the universe. The concept of an instantaneous rate of change, so central to physics, becomes ambiguous at the Planck scale. This is not a minor technical hurdle, it is a foundational crisis for our models of reality. We would need to reinvent the mathematical language of physics from the ground up. The challenge is to create a new kind of calculus, a discrete or quantum calculus, that can describe how things move and change on a lattice or a network, rather than on a smooth sheet. This is not about simply replacing a smooth curve with a staircase approximation, like a digital artist using pixels to draw a circle. That is just an approximation of the old, continuous idea. The true task is far deeper. We must discover the fundamental laws of dynamics that are native to a discrete reality. What are the natural rules for how information or geometry propagates from one quantum of space to its neighbor? How does curvature emerge from the way fundamental loops connect? The new mathematics would not approximate smoothness. It would generate the appearance of smoothness as a large-scale consequence of a more fundamental, granular logic. This would be a revolution as profound as the invention of calculus itself, forcing us to rebuild our understanding of motion, fields, and forces with a new set of tools that respect the pixelated heart of the cosmos. This computational vision forces us to confront a critical puzzle, one that has become the central proving ground for any theory of discrete spacetime. If the universe is made of grains, why doesn't it look like a grid? Imagine a simple digital image, its pixels arranged in neat rows and columns. If you rotate that image by an angle that doesn't align with its grid, the straight lines become jagged, ugly staircases. The image has a preferred set of directions defined by its underlying pixel structure. This is the fundamental problem for a grainy universe. If spacetime has a fixed, rigid lattice structure at the Planck scale, like a cosmic graph paper, then it would inherently pick out preferred directions. Experiments would detect that the laws of physics are not the same if you rotate your laboratory, because the axes of the universe's hidden grid would break the perfect rotational symmetry we observe. Even more troubling, it would violate Lorentz invariance, the deeper symmetry that includes the constancy of the speed of light for all moving observers. A fixed grid would define a special frame of reference, a state of absolute rest relative to the lattice, contradicting a century of relativistic physics. This is the major technical hurdle. A naive, brute force pixelation of space fails spectacularly because it shatters the very symmetries that make our universe coherent and predictable. The challenge, therefore, is not just to make spacetime discrete, but to invent a form of discreteness that has no fixed background, no master grid imposing its will on reality. This is where theories like Causal Set Theory and loop quantum gravity reveal their subtle genius. They do not build space out of points on a pre-existing grid. In Causal Set Theory, the universe is just a cloud of events with causal connections. There is no background geometry to give preference to any direction. The set is fundamentally random in its arrangement, with no fixed distances or angles at the fundamental level. Lorentz symmetry, the smooth rotations and boosts of relativity, is not built in, but it miraculously emerges when you look at the large-scale statistical pattern of a vast number of these events. It is a symmetry of the collective, not of the individual grains. Similarly, loop quantum gravity describes space as a spin network, a web of interconnected loops. This network is not embedded in a background space, it is space. Its connections define geometry dynamically, and the network is constantly evolving. At the Planck scale, it is a wildly fluctuating quantum foam. There is no static lattice, only a probabilistic tapestry of possible connections. The beautiful, smooth symmetries of Lorentz invariance arise as an average, a consequence of the incredibly complex and numerous ways these loops can weave together to create what we perceive as empty, flat space on large scales. This is the critical, non-negotiable test for any viable theory of quantum gravity. It must possess a form of discreteness that is background independent, where the fundamental ingredients do not live on a stage, but constitute the stage itself, in such a way that all the cherished symmetries of Einstein's relativity emerge naturally from the chaos of the quantum deep. A theory that fails this test, that imposes a rigid, microscopic grid, is a theory of a different, simpler universe, not our own. The search for the grain of reality is paradoxically a search for a grain that hides its own orientation so perfectly that the cosmos appears perfectly smooth and symmetric to every observer within it. The universe's hidden grain would leave a whisper in the oldest light. To hunt for it, scientists have turned their telescopes toward the cosmos's most violent and brilliant explosions, gamma-ray bursts. These cataclysmic events, often marking the birth of a black hole or the collision of neutron stars, act as nature's ultimate particle accelerators and precision clocks. They fire a furious beam of light across the cosmos, a flash containing photons of wildly different energies, from low-energy radio waves to the highest-energy gamma rays. In a perfectly smooth, Lorentz symmetric universe, all these photons, despite their different energies, should travel at exactly the same speed through the vacuum of space. They are all light, after all. They should arrive at Earth simultaneously, having traversed billions of light years together. But if spacetime has a granular structure, that perfect harmony could be broken. The idea is that a photon with a higher energy, and thus a shorter wavelength, might interact ever so slightly more with the fine-grained texture of spacetime itself. It is like running over two different surfaces. A long wavelength radio photon with its gentle, rolling wave might glide over the granularity as if it were smooth pavement. But a high-energy gamma-ray photon with its frantic, tiny wavelength might feel every bump and grain, slowing it down by a minuscule amount. Over a journey of billions of years, that incredibly tiny delay could accumulate into a measurable difference in arrival time. The test is stunningly simple in principle. Observe a distant gamma-ray burst, precisely measure the arrival times of its highest energy photons, and compare them to its lower energy ones. Look for a lag. The greater the distance the light has traveled, the more time there is for the effect to build up, making the most distant bursts the most sensitive probes. The precision required is almost beyond comprehension. We are talking about potentially detecting a delay of mere milliseconds, or even less, in a signal that has been traveling for over 10 billion years. It is the ultimate test of patience and precision. Observatories like the Fermi Large Area Telescope orbiting Earth and ground-based instruments like the MAGIC telescopes have been conducting this search for years. They have collected data from numerous gamma-ray bursts, some from the very edge of the observable universe. The result so far is a profound silence. No consistent lag has been found. The high-energy photons arrive in lockstep with their lower-energy siblings across billions of light-years. This null result is not a failure. It is one of the most stringent constraints ever placed on the nature of quantum gravity. It tells us that if spacetime is granular, its grain must be so fine, or its symmetry-preserving properties so perfect, that it leaves no fingerprint on the flight of light across the cosmos. Each new burst that arrives without a delay pushes the possible scale of discreteness closer to the Planck length itself, or forces theories to explain how Lorentz symmetry can emerge so flawlessly from a digital substrate. The hunt continues, with every distant flash of cosmic violence offering a chance to read the hidden text of reality. While gamma-ray bursts scan the cosmos, another search unfolds much closer to home. Inside highly controlled laboratories, scientists are building instruments of almost impossible sensitivity, devices designed to measure the fabric of space itself for the faintest tremor. These are not telescopes but interferometers. Their method relies on a beautiful principle of wave interference. Take two identical waves of light or matter. Send them along different paths, then bring them back together. If the paths are exactly the same length, the waves will reinforce each other, creating a bright signal. But if one path is even slightly longer by a fraction of the wave's wavelength, the waves will cancel each other out, creating a dark signal. This makes an interferometer an exquisitely sensitive ruler, capable of measuring changes in distance far smaller than the width of an atom. Modern versions of these devices push this precision to its absolute limit. Matter-wave interferometers, for instance, do not use light. They use atoms or even entire molecules, exploiting their quantum wave-like nature. They split a cloud of ultra-cold atoms into two paths, let them travel, and then recombine them. The resulting interference pattern tells a story of the journey, sensitive to the tiniest shifts in the gravitational field or the geometry of the space they traversed. Similarly, laser-based gravitational wave observatories like LIGO are, at their heart, gigantic interferometers. Their 4-kilometer-long arms can detect a change in length 10,000 times smaller than a proton, a feat that allowed us to hear the collision of black holes for the first time. Now, physicists are asking if these same tools can listen for the quietest possible sound, the faint rustle of spacetime's underlying grain. The hypothesis is direct. If space is not a smooth continuum but a kind of dynamic foam or a fluctuating network at the Planck scale, then the very concept of a fixed, stable distance becomes fuzzy at an unimaginably tiny level. The distance between 2 points would not be a single, eternal number. It would exhibit minute, random jitters. It would be as if you were trying to measure the distance between two buoys on a perfectly calm ocean with a ruler. But at the quantum scale, the ocean's surface is never perfectly calm. There is a fundamental stochastic froth, a seething of geometry itself. An interferometer, with its laser beams or matter waves traveling back and forth, would be constantly measuring a distance that is subtly, randomly fluctuating. Over time, these fluctuations would introduce a characteristic noise into the interference pattern, a signature of spacetime's turbulent foundation. This noise would be different from all other known sources of vibration, from passing trucks to quantum noise in the laser light itself. It would have a specific statistical fingerprint predicted by various models of quantum gravity. The experimental challenge is monumental. It requires isolating these instruments from every conceivable earthly disturbance, cooling components to near absolute zero to quiet atomic motion, and collecting data for long periods to see if any residual, unexplained noise remains that matches the theoretical predictions of a foamy spacetime. So far, the silence in these laboratories mirrors the silence from the cosmos. No definitive signal of spacetime foam has been found, yet this null result is itself a powerful guide. Each experiment that fails to detect the predicted noise pushes the possible scale of the granularity closer to the Planck length, or forces theorists to refine their models of how a discrete spacetime can appear so perfectly smooth. It is a meticulous, quiet revolution, conducted not with giant telescopes pointed at the void, but with beams of light and clouds of atoms in vacuum chambers, patiently listening for the heartbeat of a pixelated universe. The silence from our most sensitive instruments tells a profound story of its own. It suggests that if our reality is built from grains, they are woven together with such exquisite perfection that the seams are invisible even to our sharpest probes. This leads us to a staggering philosophical conclusion, one that reshapes our understanding of existence itself. The smooth, continuous, infinitely detailed cosmos we experience may not be the fundamental truth. It could be a magnificent and convincing illusion, an emergent approximation. Think of a breathtaking digital photograph on your screen. From a normal viewing distance, you see a seamless image with gentle gradients of color and smooth curves. But zoom in far enough and the illusion breaks. You see the individual pixels, the square blocks of color that constitute the whole. The smoothness was never in the picture itself. It was in your perception of it, a property that emerges from the collective behavior of countless discrete parts. If spacetime is granular at the Planck scale, then our entire reality is that digital image, the continuous fabric of space, the flowing river of time, the very idea that any distance can be halved forever. These are not features of the universe's bedrock. They are the large-scale, emergent properties that arise because we are colossal beings composed of trillions upon trillions of atoms, utterly unaware of the microscopic tiles beneath our feet. Our brains and our instruments are calibrated to a world of averages, where the quantum graininess of geometry is smoothed over into the familiar continuum. This turns a deep metaphysical assumption on its head. For centuries, mathematics and physics have been guided by the ideal of the continuum, the concept of an infinite set of points with no gaps. This ideal is powerful, beautiful, and incredibly useful. It allows us to calculate planetary orbits and model fluid dynamics with breathtaking accuracy. But we must ask a haunting question. Does the mathematical continuum, with its perfect, infinite divisibility, actually exist in the physical world, or is it a sublime invention of the human mind, a perfect tool that we project onto a universe that is, at its heart, digital? The equations of general relativity are written in the language of smooth manifolds, a language that assumes this continuum is real. Yet if the deepest structure of space is discrete, then those equations, for all their predictive power, are not describing fundamental reality. They are describing an extraordinarily good approximation of it, valid only at scales vastly larger than the Planck length. They are like a brilliant theory of the smooth appearance of water, successful in predicting waves and currents, yet completely unaware that water is made of molecules. This forces us to reconsider the nature of infinity in physics. Singularities, those points of infinite density in black holes and the Big Bang, have long been seen as physical places where our laws break down. But in a discrete reality, they may be mathematical phantoms, artifacts that appear only when we mistakenly apply a smooth, continuous model to a granular system. True physical infinities may not exist at all. There might only be very large numbers and a maximum possible density set by the grain of space itself. The infinite becomes a conceptual tool, not a physical state. This philosophical upheaval touches the core of the scientific endeavor. Science seeks to uncover the fundamental laws of nature. But if our most successful theories are approximations of a deeper, digital code, then we are in a position akin to ancient astronomers creating elaborate models of celestial epicycles. Their models worked. They predicted the motions of planets with reasonable accuracy, but they were describing the appearance of the solar system from Earth, not its fundamental structure. Our smooth spacetime theories may be the modern equivalent, brilliantly accurate maps of the cosmic appearance, yet still missing the true territory of quantum geometry. This does not diminish their value, it reframes their meaning. It suggests that the quest for a final theory is not about finding a more elegant equation in the old language, but about learning to speak the universe's native tongue, a language of discrete steps of information, of connections rather than coordinates. The continuum we cherish may be the grandest emergent phenomenon of all, a cosmic sleight of hand so perfect that for millennia, we never thought to question the solidity of the stage beneath us. The grandest illusion of all may be the universe's own origin story. If the Big Bang was not a singular beginning from nothing, but a quantum bounce from a prior state, it leaves a profound question hanging in the void. Could the echo of that transition still be detectable today, a faint scar on the oldest light in the cosmos? This light is the cosmic microwave background, the afterglow of the hot, dense plasma that filled the infant universe. For decades, cosmologists have studied this faint radiation as a baby picture of the cosmos, mapping its tiny temperature variations that would later seed galaxies. A smooth, singular beginning predicts a specific statistical pattern in these fluctuations, but a quantum bounce, a transition from contraction to expansion, governed by the granular rules of a discrete spacetime, could write a different signature into that ancient light. The violent, quantum geometric processes at the moment of the bounce might have imprinted unique patterns, perhaps a preferred direction in the sky, specific shapes in the temperature variations, or a telltale cut off in the spectrum of gravitational waves from that primordial era. These are not just theoretical speculations, they are potential observational targets. Space telescopes like Planck have already mapped the cosmic microwave background with exquisite detail, and future missions will probe it even further. The search is on for anomalies that cannot be explained by standard smooth inflation, fingerprints of a universe that was born not from a singularity, but from a quantum leap of geometry. Finding such a signature would be the ultimate archaeological discovery, unearthing not a fossil, but a direct image of spacetime's quantum nature at the moment of cosmic rebirth. This transforms cosmology from a study of the past into a direct test of quantum gravity itself. But the implications of a granular beginning stretch even further into the realm of the truly vast. Our leading model for the universe's early rapid expansion is called cosmic inflation, a period of exponential stretching that smoothed and flattened the cosmos. Inflation is a powerful idea, but it rests on speculative physics, a hypothetical field whose properties must be finely tuned. A discrete spacetime could provide the natural mechanism inflation lacks. In a quantum gravitational framework like loop quantum gravity, the repulsive force that drives a cosmic bounce is not a one-time event. It could manifest as a natural phase of accelerated expansion, a quantum geometric inflation built into the fabric of reality itself, requiring no ad hoc fields. The granular structure of space at that epoch would determine how this inflation began, how it ended, and what kind of universe it produced. This leads to a staggering possibility, one that redefines the meaning of everything. If the fundamental quantum geometry can exist in a vast landscape of possible configurations, and if a quantum bounce or inflationary period can happen not once, but in countless regions of a larger meta-reality, then our universe may be just one page in an infinite cosmic library. This is the multiverse. In a continuous space-time, the concept of a multiverse often relies on abstract, untestable mathematics. but in a discrete reality, it gains a concrete physical mechanism. Different patches of quantum geometry could crystallize into different stable vacuum states, each with its own effective laws of physics, its own values for the constants of nature, its own number of spatial dimensions, even its own particle content. Our universe, with its 3 dimensions of space and its specific set of forces, would be one possible outcome in a vast ensemble of quantum geometric possibilities. Some regions might inflate forever, others might collapse quickly, and some, like ours, might find a precarious balance that allows for stars, planets, and life. This is not a random collection of unrelated worlds. They would all be born from the same fundamental rules of discrete quantum gravity, just as countless different structures can be built from the same set of Lego bricks following the same principles of connection. The multiverse becomes less a philosophical speculation and more a natural consequence of a universe built from dynamic, granular geometry. It suggests that the peculiar fine-tuning we observe in our cosmos, the seemingly perfect balance that allows for complexity, might not be a miraculous accident, but a statistical inevitability in a cosmos where every possible configuration of physical law eventually manifests somewhere. The search for the grain of space, therefore, is not just about the very small. It is a key that could unlock the architecture of the very large, revealing whether our cosmic home is a solitary island or one shimmering thread in an unimaginably vast and varied tapestry of realities. A confirmed granularity of spacetime would not end the story of physics, but begin its next most radical chapter. The long-term trajectory would point toward a fundamental paradigm shift, one that redefines the very ingredients of reality. For centuries, our most basic objects have been particles and fields. We imagine electrons as tiny dots and the electromagnetic field as a smooth, continuous entity that fills space like an invisible fluid. These concepts exist within the container of spacetime. But if spacetime itself is not the container, but the emergent picture, then particles and fields cannot be fundamental either. They too must be secondary phenomena. The new fundamental objects would be something far more abstract, yet potentially simpler, relationships in a vast network or quantum bits of information. Reality would be described not by fields vibrating in a geometric arena, but by the pattern of connections between elementary nodes, by the entanglement structure of quantum information. Think of it like the difference between watching a movie and reading the script. The movie is the vivid, continuous experience of particles moving through space and time. The script is the underlying code, the list of characters, their relationships, and the sequence of scenes. A discrete universe suggests we have been mesmerized by the movie, and the future of physics is about deciphering the script. This shift is profound. It moves us from a physics of things located somewhere to a physics of pure structure. Location itself becomes a derived concept, something that emerges from the pattern of connections, not a primary property. The question, where is it, would be answered not with coordinates but by tracing its relational web within the cosmic network. This does not render the physics of the last 3 centuries wrong, any more than Einstein's relativity rendered Newton wrong. Newtonian mechanics remains astonishingly accurate for describing baseballs, bridges, and spacecraft. It is an extremely effective theory, a magnificent approximation that works perfectly within its domain of medium speeds and scales. Similarly, our current framework of quantum field theory and general relativity in a smooth spacetime is arguably the most successful effective theory ever devised. It predicts the outcome of particle collisions to a dozen decimal places and guides satellites with pinpoint accuracy. Its power and precision are undeniable. Confirming discreteness would not invalidate these triumphs. It would simply reveal their true domain of applicability, the macroscopic world where the grains of reality are too small to notice. The challenge for future physicists would be creative and monumental, building a new physics from the discrete ground up. They would need to derive, not assume, the smooth continuum of space, the flow of time, and the particles we see, showing exactly how these illusions arise from the dance of information. It is an open frontier of unimaginable richness, where the most familiar aspects of our world become puzzles to be solved anew, emergent wonders from a deeper, stranger truth. The seamless stage of reality we take for granted is a powerful, unproven story. Our journey has revealed that if this story of infinite smoothness is wrong, the consequences are not a single correction but a cascade of transformations. The terrifying singularities at the heart of black holes and the dawn of time would dissolve into extreme yet knowable quantum states. Motion itself would be freed from Zeno's ancient paradox, becoming a progression of fundamental steps. The perfect conservation laws and symmetries we hold sacred would be revealed as magnificent approximations, emerging from a deeper digital order. Our most powerful mathematical language, calculus, would need reinvention to describe a world that cannot be divided forever. We are asked to shift our entire perspective from a cosmos of smooth flows and continuous fields to a universe of discrete clicks and quantum connections. This suggests a profound truth about the nature of reality itself, that what feels most solid and continuous may be the grandest emergent illusion, a collective effect born from countless grains of information or geometry. This is not science fiction, but the cutting edge of science. It is a frontier driven by the quiet logic of theorists and the exquisite precision of experiments, from telescopes scanning distant gamma-ray bursts to interferometers listening for the faint hum of spacetime foam. The search for the true fabric of the cosmos continues, a quest to see if the universe is written in the language of the infinite or in the finite, elegant code of the quantum.